Hello, so in this video I'm going to take you through the 2019 Higher Chemistry paper. You may want to have a data booklet handy and also a calculator while going through this, and feel free to skip forward to any question that you specifically need help with. So question 1 is testing your knowledge on what a non-polar covalent bond is. So that's a bond where the atoms in the bond have the exact same electronegativities, which results in the shared pair of electrons being shared equally. So if you look up the electronegativity value of hydrogen in the data booklet, you will find that it's 2.2. Therefore, it will form a non-polar covalent bond with an element that also has the electronegativity of 2.2. So the answer is C for that one. Question 2, we're looking for a polar molecule. So if a molecule is polar, it would need to contain polar bonds. And it needs to be asymmetrical. That's why I'm spelling symmetrical. Okay, so if it's not both of these things, then it won't be polar. So if we draw the molecules, it's the easiest way to see if it's polar or not. So carbon tetrachloride. Now, if you look up the electronegativity values of the elements, first of all, to find out if there's any polar covalent bonds, you would find chlorine's more electronegative than carbon, so that means the chlorine would carry a delta minus, partially negative charge, and the carbon ends up being delta positive. So this does have polar covalent bonds in it. However, a tetrahedral structure is symmetrical as long as it's the same thing around the outside. So because there's 4 chlorines around the outside, that is actually a symmetrical shape. Therefore, that molecule is non-polar. Okay, so A is not our answer. Then if we draw ammonia, NH3, so we've got nitrogen, hydrogen, 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 and nitrogen is more electronegative than hydrogen, so that carries the delta minus charge, leaving the hydrogen's delta positive. So a trigonal pyramidal molecule, which is what this ammonia is a non-symmetrical shape, it's asymmetrical. Therefore, because it's got polar bonds in it, it is a polar molecule. So B is our answer. If you don't understand how this is an asymmetrical shape, if you draw a line of symmetry through the middle of the space the molecule takes up on both axes. So if we look at the horizontal plane of symmetry, there's a side of the molecule that's all delta plus, and then a side that's delta minus. So that's 2 oppositely charged sides of the molecule, which means that it is polar, has a permanent dipole established. Okay. If we just draw the rest, just so you can see how they are not the correct answer. So carbon dioxide, remember, is a carbon with double bonds to oxygen. So oxygen's more electronegative than carbon, so that's delta minus, carbon's delta plus, and then this other oxygen is also delta minus. So this does have polar bonds in it. However, this is a linear molecule, and linear molecules are always symmetrical. So because it's a symmetrical shape, the dipoles cancel out, and overall it's a non-polar molecule. So C is not our answer either. And then if we look at the last one, methane, CH4, that's very similar to carbon tetrachloride, except in this case, the carbon is the most electronegative atom in the bonds, so that's delta minus this time. And the hydrogens are delta plus. Okay, and again, it's a symmetrical shape because you've got hydrogens all around the outside that are all delta plus, so the dipoles would cancel out in this case as well, giving you a non-polar molecule. Yeah, so B was our answer there. Then number 3, which of the following is most likely to act as a reducing agent? So when it comes to reducing agents, you are looking at the top right corner of the electrochemical series. In the data booklet. Okay, so all of the reducing agents would be found at the top right. If you looked up the electrochemical series, you would find that only B and D are listed in there, and they're at the bottom left corner, and that's where the best oxidizing agents are. So permanganate and dichromate, which is what B and D are actually oxidizing agents, so they are not accepted answers as a reducing agent. So top right for reducing agents, bottom left for oxidizing agents. Carbon monoxide and hydrogen peroxide are not shown in the electrochemical series, so the easiest way to work it out is to think about what they naturally become. So carbon monoxide can quite easily become carbon dioxide if it reacts with more oxygen. I'm not going to balance this equation. Okay, so that has gained oxygen, which means it's oxidized. And as you should know, for agents, they're always the opposite agent, whatever reactions happen to them. So reducing agents become oxidized and oxidizing agents get reduced. So because the carbon monoxide is easily oxidized, that makes it a good reducing agent. So A is our answer. But if we look at hydrogen peroxide as well, hydrogen peroxide breaks down into water and oxygen. Okay, so it's lost oxygen, which means it's been reduced. And because it's been reduced, that makes it a good oxidizing agent. So hydrogen peroxide is an oxidizing agent as well. I would encourage you to add these to your data booklet. So I would write carbon monoxide at the top right-hand corner of your data booklet. And then I would put hydrogen peroxide down at the bottom left, just so you can remind yourself. It might go into your head via osmosis, which has nothing to do with chemistry, more biology, that they are oxidizing and reducing agents, respectively. Okay, and then question 4. So you're given 2 half-ion electron equations for this redox reaction, and it asks how many moles of zinc are oxidized by 1 mole of nitrite ions. So, or nitrate ions, sorry. So what you need to do here is write a balanced overall electron redox equation first, so that you get the stoichiometric molar ratio from the reaction. So it's just kind of like simultaneous equations in maths, and you would have done this in National 5. You just need to get the electrons to cancel out. So we need to times this top equation by 2 and times this bottom equation by 3. So that means when you times everything in that equation, so that means there's a 2 there, an 8 goes there, and that becomes a 6, and then a 2 and a 4 for the water. And then here we've got a 3, and a 6. So now you can see there's 6 electrons in each equation, so they would cancel out. You can write the overall redox equation out fully again, but you don't really need to, because all you need is the molar ratio. So you've got NO3 minus, that's 2 in the ratio, and zinc is a 3 in the ratio. So in the question, you're told you have 1 mole of the NO3 minus. So if you apply the molar ratio, that means you can oxidize 1.5 moles of zinc in the 2:3 ratio. So you would divide by 2 times by 3. Okay. Or you can, if there's another way you can work out the ratio, then just use that. But as long as you get the answer at 1.5. Okay, next question. Clear off these drawings. Scroll down. So, question 5, which of the following is a tertiary alcohol? So you can draw these out if you want to, but there's quicker ways you can do it from the names. So a 1-ol is always a primary. Okay, so anything that's 1-ol will always be primary, so A is not the answer. 2-methyl butane 2-ol, so that is got to be at least a secondary or a tertiary, because the hydroxyl is not the end of the chain. There is a branch on the same carbon as the hydroxyl group, which means it will definitely be a tertiary alcohol. Okay, so B is our answer. C, if we just go through the rest, it's got the hydroxyl in the middle of the chain, but there's no branch attached to the carbon that the hydroxyl's on, so that's just a secondary. And then for D, there is a branch, but it's not attached to the same carbon as the hydroxyl group, so again, that's just a secondary. alcohol. Okay, so for it to be tertiary, you really need the branch on the same carbon as the hydroxyl group. Then question 6, which of the following could be produced by partial hydrolysis of X? So when you hydrolyze, or for a hydrolysis reaction, you'll break either an ester link or an amide link. So this molecule here has amide links in it, Tron groups. Okay. So they'll be broken. If it's partial hydrolysis, then you're only breaking one of them. So I'm going to break this one first, and it's giving us the options of dipeptides. So what you're looking for is to see if you can see this molecule underneath. Now, what you need to remember is this NH becomes NH2 because the hydrogen adds back on. So it would be NH2 at the end. So you're really just wanting to look to see if you've got the same pattern all the way along. And you can see that A is in fact that up there. Okay, so A is the answer. If you couldn't find that molecule underneath, that dipeptide underneath, then what you do is look to see what you get by breaking this one. So just remember this carbonyl, what looks like a carbonyl actually ends up as a carboxyl when you complete the hydrolysis. So you'd be looking to see if this could be found underneath here, which it can't. Okay. And then question 7, a compound with a molecular formula C6H12O2 could be, so needs to have 2 oxygens, and the only groups that we really know of that contain 2 oxygens in them are the esters and carboxylic acids. So B is a ketone because it ends in -one, and that contains a carbonyl group which only has 1 oxygen, so it's not going to be B. And then C is an alcohol which contains a hydroxyl functional group. So again, that's only going to contain 1 oxygen, so it's not going to be C either. So then we're left to decide between A and D. So this is going to really come down to the number of carbons. So A is an ester because it's got the name like an ester, it ends in anoate, and it's got the "-ile" in the first part. And then an ester link, remember, looks like this. So that's got 2 oxygens in it. And then D is a carboxylic acid, and we know that because it ends in anoic acid, and that's got the carboxyl functional group, which also has 2 oxygens. So this is now going to come down to number of carbons. So we're looking for 6 carbons. So if we look at A, pent equates to 5 carbons, eth equates to 2. So altogether that molecule has 7 carbons in it. So A is not going to be the answer. And then for D, hex is 6. So if it's hexanoic acid, it'll have 6 carbons and 2 oxygens, and you can just trust that the hydrogens would all work out in the end. Okay. So D was the answer there. And then question 8. Compound X reacted with hot copper oxide, and the resulting product did not give a colour change when heated with the Fehling's solution. So if it reacted with one oxidizing agent, which is what hot copper 2 oxide is, but then it doesn't react with another oxidizing agent, which is what Fehling's solution is, it means that you can only oxidize this once. One time. Okay, so the type of substance that can only be oxidized once would be a secondary alcohol. So that goes from a secondary alcohol to a ketone, and then remember you can't oxidize a ketone any further. Or you could be oxidizing an aldehyde, because an aldehyde will be oxidized to carboxylic acid. Okay, so we're really looking for a secondary alcohol or an aldehyde. So A is a primary alcohol, and you can tell that because it's a 1-ol, so the hydroxyl's at the end of the chain. So A is not the answer, because that could be oxidized twice. Primary alcohols will go from a primary alcohol to an aldehyde and then to carboxylic acid. Pentan 2-ol, that's a secondary alcohol, so that's probably our answer. And then C is a ketone, you know that because it ends in -one, they can't be oxidized at all, so it's not going to be C. And pentanoic acid is a carboxylic acid, and you know that because of the name ending, and they can't be oxidized any further either. Okay, so B was our answer there. In question 9, the systematic name for this acid. So you find the longest chain of carbons that includes the functional group. So that's going to be 3, whichever way you do it. Be sure to check in L shapes. So even if I was to do it this way, that's still 3 carbons. If I was to do this way, that's still 3 carbons. So it doesn't matter which way you look at it, you're only ever going to get a chain of 3 carbons, including the carboxyl group. Okay, so that's a carboxylic acid with 3 carbons. So that means the main name is going to be propanoic acid. So that means we can rule out pentanoic acid, the ethanoic acid one. Okay, so we're now left with C and D. You here have 2 branches. Now they're 2 branches that each contain 1 carbon. Because they are separate, they're in separate circles, they don't constitute as an ethyl branch. That's where you would have the 2 carbons joined onto each other. So it'd be CH2, CH3, and then on the main chain. Okay, so it's not an ethyl propanoic acid either. And the branches are both on carbon 2. So remember, you have to number from where the functional group is. That'd be carbon 1, 2, 3 in the main chain. So it's diethyl propanoic acid because there are 2 ethyl branches. So D is our answer there. So then if we scroll down to question 10. So this is testing your knowledge of terpenes and what they're made of. So terpenes, remember, are made up of isoprene units, and isoprene units contain 5 carbons. So for it to be made up, for it to be derived from a terpene, it needs to have a multiple of 5 carbons. So this would be a terpene, this would be from a terpene, and this would be from a terpene. This 9 is not a multiple of 5, therefore D is the one that's not derived from a terpene. Okay. And then question 11, which reaction can be classified as reduction? So reduction is the opposite of oxidation. So these are all carbon-based organic compounds which you look at the oxidation of. The reduction is just going backwards. So going from an alcohol to carboxylic acid would be oxidation. Going from an aldehyde, they all end in al, to a carboxylic acid would also be oxidation. Going from a ketone to an alcohol, that's actually reduction because you're going backwards because all the oxidations tend to start from alcohols. And then propan-2-ol to a ketone, propanone, would be oxidation as well. So that means C is our answer. So 12. Secondary amine has 2 carbon atoms directly bonded to the nitrogen. So here we're looking for 2 carbons directly bonded to the nitrogen. So this nitrogen only has 1 carbon on it, so that would probably be a primary amine. This one, the nitrogen's here, and that's got 2 carbons on it, which is what we're looking for, so B is our answer. If we look at this one though, the nitrogen's here, that's got 3 carbons, so that would be a tertiary one. And D, the nitrogen's here, that's only bonded to 1, so again, that would most likely be a primary. Okay, this is a problem solving question though, because you're told what you're looking for, so you're not expected to know what a primary, secondary, tertiary amine is. You're only doing that for alcohols. Okay, then question 13. The number of moles of ions in 1 mole of copper 2 phosphate. So you need to know the chemical formula for copper 2 phosphate first. So this is going to take you back to your National 5 days. So the copper has got a valency of 2 in this case. And then phosphate, if you can't remember what a phosphate is or looks like, you can look it up in the data booklet on page 21 in the higher data booklet. So that's PO4, 3 minus. Oops. Okay, so the valency of the copper is 2, you get that from the neutral. Because phosphate's charge is 3 negative, then its valency is 3. So then you swap the valencies over, you get 3 and 2, and then you look to see if you can simplify the ratio, which you can't in this case. So you've got 3 copper ions and 2 phosphate ions. So it's these subscript numbers that give you the number of moles. So in 1 mole of copper 2 phosphate, which is what this is, you have 3 moles of copper ions and 2 moles of phosphate ions. Okay, the ions, the copper's got a 2 plus charge because its valence is 2 and the minus. So you'll have 3 moles of the 2 plus copper and 2 moles of the 3 negative phosphate, which if you add 2 and 3 together, you get 5. So there's 5 moles of ions altogether in that 1 mole of copper 2 phosphate, which is always a bit mind-blowing. So then question 14, which of the following gas samples has the same volume as 4 grams of methane? So remember, this is doing molar volume, and for molar gas volumes, if you have the same number of moles of a gas, you'll have the same volume. So really you need to calculate how many moles of each of these gases you have. So I like to use this triangle here for the relationship of molar volume. So you've got the volume of the gas up here, which has 3 meters. I don't really need this for this question. So we need to work out, because we've got masses, we've got N, M, and GFM, so N is equal to M over GFM. Okay, so you have, for the moles of methane that you've got 4 grams, and the gram formula mass of methane is 12 plus 4, 16, so that comes out as 0.25 moles. So you're looking for one down here that's also 0.25 moles. So the mass of helium, you get your gram formula mass page in the data booklet. I just need to find. So helium has a mass of 4. So for the moles of this, you've got 1 divided by 4, which is going to give us 0.25, so that's most likely our answer. For hydrogen, just remember hydrogen's diatomic, so that would be, for the moles of hydrogen, it would be 1 over 2, so that would be 0.5. For nitrogen, nitrogen is also diatomic, so that would be 3.5 over, and nitrogen is 14, so N2 would be 28. So 3.5 over 28 would not give you 0.25. So it would give you 0.125. So that's not the answer either. And then chlorine is also diatomic, so that would be 35.5 over 71, so chlorine is 35.5, which means that you've got, again, 0.5 moles. Okay, so the same moles will occupy the same volume, so because you've got 0.25 moles of methane, and you've got 0.25 moles of helium, they would occupy the same volume at the same temperature and pressure. So then question 15. So you've got 0.05 moles, sorry, 0.05 moles of magnesium carbonate. So I'm going to write that above the magnesium carbonate in the question, so 0.05. And that was added to a solution containing 0.06 moles of nitric acid. And then you're to work through these statements. So my advice for these would be to work out the moles of everything before you look through the statements. And Also, you'll notice the possible answers mention excess, so you need to really work out which is the limiting reactant first of all. So if we take the magnesium carbonate and nitric acid and use the mole ratio, so it's a 1:2 ratio. So if we want to react all of the magnesium carbonate, then we will need 0.1 moles of nitric acid. So it's a 1:2 ratio. We don't have 0.1 moles of nitric acid, we have less than that, so that means the nitric acid is the limiting because we don't have enough to react all the magnesium carbonate. Okay, which means that all the mole ratios or all the molar quantities in this reaction is based off of that 0.06 moles of nitric acid. So you still use the mole ratio because it's a 2-part of nitric acid. If you're going to react with 0.06, then that means you're only going to use 0.03 moles of the magnesium carbonate. So that's 1 part in ratio. That means you'll also make 0.03 moles of the magnesium nitrate, and you'll make 0.03 moles of water, and you'll also make 0.03 moles of carbon dioxide because they're all 1 mole in ratio. So then if we look through the statements, 0.05 moles of carbon dioxide is produced. Well, that's not true because it's 0.03. 0.06 moles of magnesium nitrate is produced. That's also not true. It's only 0.03. The magnesium carbonate is in excess by 0.02 moles. So this is how much we're using for magnesium carbonate. We have 0.05 altogether, so that is in excess by 0.02. We were to take those away from each other. So that's the answer. And then D, the nitric acid is in excess. Well, that's not true, regardless of the quantity, because we've worked out that that's the limiting. Okay. So then, question 16. Which of the following diagrams does the dotted line represent a permanent dipole interaction between propanone? So I find it useful to label the polarities on the carbonyl here. So the carbon's less electronegative, so it's delta plus, the oxygen from electronegative, so that's delta minus. So we'll label them all. You can usually ignore hydrocarbon regions because they are always symmetrical, so the dipoles will always cancel out. So I would only ever really label things that aren't hydrocarbon. So what you're looking for is a delta minus attracting a delta positive. So here we've got 2 delta minuses attracting to each other. That can't happen because it's opposites that attract, so A is not the answer. B, you've not got the dipoles interacting with each other, so that's not the answer either. Again, in C, it's not the dipoles interacting. And then for D, you've got a delta minus attracting a delta positive carbon, so that is the answer. And question 17, atom economy. So you get the equation for this in the data booklet. So on the contents page. So the equation is the mass of desired products over total mass of reactants times by 100. So if we work this out, the desired product is iron, so that's this. So you can ignore the carbon dioxide because that's not a desired product, but you always need the mass of the reactants. So we've got 4 times the mass because there's 4 moles of iron, 4 times gram per mole mass of iron, so 55.8 divided by 2 times 159.6 plus 3 times 12. And then that will be multiplied by 100. So if you put that into your calculator, let's wrap it here. If you put all that into your calculator, you will get 62.8%. So that's E. Then question 18 is to do with molar volume as well. Because the same moles of gas will occupy the same volume, you don't need to convert to numbers and moles here, you just use the volume given in the ratio. So you're told there's 100 centimeters cubed of propane and 600 centimeters cubed of oxygen. Okay, because you're given both reactants, you need to 600 units. Because you're given both reactants, you need to work out what the reactant is in excess first. So again, if you take the mole ratio of these from the equation, so it's a 1:5 ratio, propane to oxygen. So if you've want to react all of your 100 centimeters cubed of propane, then you need 500 centimeters cubed of oxygen. You have more than that, so that means that the propane is limiting. Okay, so you're actually going to only react 500 centimeters cubed of oxygen, so you're going to end up with 100 centimeters cubed left over. Okay, because the propane is limiting, that then dictates the volumes of all the other gases you end up making. So the question's asking for the total volume of gas at the end of the reaction. So water is not a gas, so you can ignore that. Don't include that because it's not a gas. And if you're making 3 moles of carbon dioxide, that's going to equate to 300 centimeters cubed, because 1 mole in the ratio is 100 centimeters cubed in this case. Okay, so you're going to react all of your propane, so that's going to disappear. You're going to use up 500 centimeters cubed of your oxygen, so you will have 100 left, and then you're making 300 centimeters cubed of carbon dioxide. So altogether, that adds up to 400 centimeters cubed of gas. The water doesn't count because it's in a liquid state. Okay, if it was a gas, you would include that as well, and that would equate to 400 centimeters cubed, because it's 4 moles, so you would end up with 800 at the end. Don't forget to add on any excess gas reactants if it asks for the total volume of gas. So, question 19, the first step gave a percentage yield of 60%, and then the second step, the yield was 90%. So this is a very odd question, to be honest. You're basically trying to find 90% of 60, because after, if you imagine starting with 100%, okay, and then you end up with just 60%, and then you're getting only 90% yield from the 60%. So to find, people find percentages differently, but you're essentially finding 90% of 60. So that could be 90 over 100 times 60, or the way I usually do it is change the percentage to decimal, so I would do 60 times 0.9, but either way you're going to get the same answer. So if you do that, that gives you 54%, so you're going to end up with an overall yield of 54% for this reaction. So then question 20, the volume of hydrogen gas given off against time when an excess of zinc lumps is added. The following graphs show the volume of hydrogen gas given off when excess zinc powder. So here we've got lumps versus powder. So because you're going to use powder, that's going to go faster. And then this time you've got the same concentration of acid, so that's not going to change the rate. But you've only got half the amount of acid. Now, the zinc's in excess, so if you're going to decrease the volume of the acid, then that is going to change the amount of hydrogen you make. So you're only going to make half the amount of hydrogen because you have half the volume of acid with the same concentration. That means that we want the hydrogen gas, like the end volume of hydrogen, to be at this line. That rules out A, and it also rules out D. So then we're between B and C, so we've changed from lumps to powder, which means the rate's going to increase. So that means the curve should be steeper, so it needs to be C, because B is going at the same lower rate, but lesser gradient. Okay, So that's is testing your knowledge on controlling the rate of reaction. Then 21 is to do with Hess's Law. So for this is looking for what B is, if you look at all the potential options. So that's going from here to here. So the alternative pathway would be to go from W to X, and you're going along that direction. So that means A stays as it is. And then we're going from X to Y. Now that's going backwards across the arrow. So that means you're taking away C. And then from Y to Z, which again is going backwards to where the arrow is pointing in the diagram. So that would be then minus D. So that means our answer is A. Question 22, which of the following is not a factor that affects the rate of a reaction? So activation energy will affect it, because if the activation energy is higher, the reaction will be slower. If the activation energy is lower, the reaction is most likely faster at a given temperature. The kinetic energies of the reactant molecules, well, that's important, because if you have lots of particles that have energy greater than or equal to the activation energy, then the reaction will be faster. Or if there's less particles that have the sufficient energy, then it will be slower. So B is not an answer, because that does affect the rate. The concentration of reactants, well, we know from National 5 that concentration affects the rate. As the concentration increases, the rate of the reaction will increase. And enthalpy change. So enthalpy change for a reaction is the difference in energy between the reactants and the products. So that is fixed for a given reaction, it doesn't change. So that's not going to affect the rate at all. It's only the activation energy that would make a difference. The enthalpy change is always fixed. So then question 23. Which of the following reactions would the yield of product be increased by lowering the pressure? So this is to do with the equilibrium. Low pressure favours high moles of gas. So anything to do with pressure and equilibrium only affects gases. So anything that's a solid can be ignored. You basically want to calculate the number of moles of gas on each side of each reaction. So for A, you've got 2 moles and 2 moles, so that actually won't be affected by pressure, because the number of moles of gas are the same on both sides of the reaction. Here we've got 4 and 2. So an increase, lowering pressure would actually shift the equilibrium left in this case in favour of the reverse reaction, because low pressure favours high moles of gas and there's higher moles on the left hand side. And C, we've got 1 mole and 2 moles. So this would be our answer, because if we're lowering the pressure, that's going to favour the side with more moles. So that would favour the right hand side in this case, which favours the forward reaction and increases your yield. And in D, we've got 3 moles and 1 mole. So again, lowering the pressure would actually shift the equilibrium left in favour of the reverse reaction here, which would decrease your yield. So the answer there is C. Question 24. Which graph would show the effect of increasing temperature? So temperature changes the kinetic energy of the particles. The only thing that can affect the activation energy is the catalyst. Okay, so that activation energy line is not going to move, which means that C can't be an answer, because it's shifted back to show the catalyst being added. So if you are increasing the temperature, you're going to increase the average kinetic energy of the particles. So basically, if you think of this curve as a pile of sand, you're going to shift the pile of sand across to the right, and it would look something like that. Okay, so the one that shows it being shifted over like a pile of sand is A. Okay, B, it's showing, B and D are showing that there are more particles present, because there's more underneath, or D showing more particles present because there's more area underneath the curve, and the increasing temperature won't increase the number of your molecules. And B is actually showing a slight decrease in the temperature, because the keep shifted to the left. So that's not the answer either. And then question 25 is our problem solving question. So alkenes react with ozone to form ozonite, which can be decomposed to their carbonyl compounds. Which of the following alkenes would produce a mixture of ethanol and propanol? So I would always draw out the things it's telling you. So ethanol, you draw them like this. These are drawn. Make it a bit easier. So ethanol would be 2 carbons as an aldehyde, and then propanone would be CH3 and then CH3 there. So if we look at what happens, this double bond essentially forms 2 carbonyl groups. So what I'm going to do is, and obviously this is going to be a very long double bond. So that's what we must have started with. So if you look at the possible answers, we've got CH3, CH, and then, so it's not A, CH3, CH, not CH, so it's not B, CH3, CH is not C either, and then CH3, CH, C with a CH3 and another CH3, so it must be D. Yeah, so scribbling out molecules on these questions can definitely help. And that concludes the multiple choice part of this paper.